Welcome to this, the fourth video in a series regarding Maths Methods 3 and 4 revision. This one dealing specifically with Chapter 2, Revising Linear Functions and Matrices. As usual, please note the questions and examples used in this video are taken from the Cambridge Essential Mathematical Methods 3 and 4 CAS textbook. No intention has been made to infringe copyright, and my apologies if it has. This is simply a video resource for my current students to assist in their preparations for their VCE examination. Thank you for your understanding. There is a lot in the particular textbook that we're dealing with at the start of the chapter with regard to linear relations, basic solving of equations, and more specifically coordinate geometry. I recommend that rather than going over the same content twice, you look back at the other videos on Maffs Guru with regards to the coordinate geometry, and there's a pretty detailed explanation of each of the various concepts. I think at this moment we'll just concentrate on the ideas behind the matrix algebra. So what is a matrix? Well, a matrix is any collection of numbers in the square brackets. And if, for example, I was to have the numbers 0, 1, 2 and 3, then what I would find is that this is defined as a 2 by 2 matrix. All right? That is called the order. And why is it 2 by 2? Because it's two rows and two columns. How do you remember which one comes first, rows or columns? Well, the way I remember it is perhaps a little rude, and it's RC, yes? As in, I'm feeling a bit RC today, or RC, so rows and then columns. If we want to try and multiply these things together, then what we have to do is make sure that a 2 by 2, for example, and these are normally written in brackets, and a 2 by 6 will in fact multiply together because these two middle values here are the same. They can only multiply if the row of the second is equal to the column of the first, or the column of the first is equal to the row of the second. And what order of matrix will that give you as a result? Well, it gives you the 2 by 6. So that will give you a 2 by 6 matrix. How do we multiply these things together? Well, if we come up with a swift example of 1, 2, 3, 4, and we'll multiply that by 1, 2, then let's just check our order first. This is the 2 by 2. How many rows does this have? How many rows has this got? It's got 2. How many columns? 1. Can we actually multiply this together? Yep, because the 2 and the 2 are the same. And that means we're going to end up with a 2 by 1 answer. So we're going to end up with a 2 by 1. And how do we do this? Well, you do the 1 times the 1 and the 2 times the 2, and you add them together. And as I remember it, you work across and down that one. So 1 times 1 plus 2 times 2 gives you 5. And the same thing here, you work across and the same down in that one. So 3 times 1 is 3, and 4 times 2 is 8, and add those together and you get 11. So that was relatively simple, right? You must make sure that you get your rows and columns the right way around. What if I wanted to add and subtract matrices together? Well, if I have the matrix 0, 1, 2 and 3 and I want to add it to the matrix 1, 2, I can't do that. Right? To be able to add matrices together, they've got to be exactly the same size. So because this is a 2 by 2, I would have to add it to another 2 by 2. So let's make this a 2 by 2 by getting rid of that, and we'll add 4 and 6 in there. And adding or subtracting matrices is incredibly simple because all you do is add the same elements. This element here and that element there are in the top left-hand corners, add them together. The 1 and the 4, add them together. 2 and 2, add them together. And 3 and 6, add them together. And there we go. We have matrix addition. Oh, this matrices stuff is relatively easy. Quick skim by what the identity matrix is. An identity matrix I is given by a matrix where all of the numbers are zeros, barring the diagonals, which are ones. All right? So this would be a 3 by 3 identity matrix because the diagonal through the matrix from top left to bottom right are ones, and everything else is zeros. Now, this identity matrix is actually quite important to us because if you remember, we use it for matrix multiplication, or more specifically, matrix division. Not that you can actually divide matrices. One last thing to be able to note, and there is a huge difference here you need to know, and that is the determinant of a matrix, all right? So let's say we're looking for the determinant of matrix A, and what is matrix A? Well, we'll come up again with 1, 2, 3, and 4. Our determinant is given by the value of AD minus BC. Now this isn't here to teach you matrices, this is just to remind you, and if you remember, this is A, B, C, and D in that order. So AD, so you multiply your diagonals, which would give you 4, and you take away the multiplication of the other diagonals, right, which would be 6. So the determinant of this would be minus 2. That is not to be confused with what you do when you inverse, where you have 1 over the determinant. Please remember, the determinant is AD minus BC. So having dealt now with the basics, what else do we need to know? Well, the thing that tends to throw is the language that's used in matrices. Right? So a square matrix is said to be regular if there is an inverse. Right? Now if you can inverse a matrix, then it is said to be regular. So if I look at the matrix 1, 2, 3, 4 again, and remember, if you want to inverse it, what do you need to do? Well, to inverse, you swap these two corners and you make these two things negative. So that's the first rule, or that's the first part. So 4 and 1 swap, and whatever is in those corners become negative, or you inverse the sign of them, because if they're already negative, right, then we have to work out what goes in front, and this is where we work out the determinant. Now we already know the determinant of this matrix, and we'll call it A again, was equal to AD, which is 4 times 1, which is 4, minus these two together, which is 6, so that gives you negative 2. And to work out the inverse, the fraction, there is a fraction that goes in front of this, is equal to 1, right? This value here is 1 over the determinant. So in which case, if we now finish this off, we have 1 over minus 2 multiplied by 4 minus 2 minus 3, 1. It's okay to leave it like this, but most of the time the book will write it in a different way, whereby it will multiply this value here by each of the terms inside the matrix. What will that give us? Well, minus a half of 4 would give us minus 2. Minus a half of minus 2 would give me minus 1. That would give me 3 over 2. And hopefully we'd all be happy that that would be minus a half, right? So that is our inverse of a matrix. How does that help us? Well, we'll just do some examples shortly. Square matrices, right? Remember, you can only work out the inverse of square matrices, all right? You can only work out the inverse of square matrices. And if a square matrix does not have an inverse, right? If it does not have an inverse, and normally that's given because the determinant of A becomes equal to 0. I'll say it again. The square matrices which do not have an inverse are called singular matrices, right? And that is because the determinant becomes equal to 0. So something else that's quite important that you should remember is the word singular. And as with everything that we do in maths methods, and particularly the CAS course, you can use your CAS calculator. And a big hint now is to make sure that you understand how to use your CAS for the examination, because it could save you a huge amount of time. Now, how do we actually use this inverse? Well, here's an example. And the algebra is probably the most important part, or the matrix algebra is the most important part. If we have the matrix A given by 3, 2, 1, and 6, and I have the idea that YA is given by 5, 6, 7, 2, and it wants me to find Y. To be able to find the Y, we've got to get rid of this A, all right? Now, we can't divide matrices, right? We can multiply them, we can add them, we can take them away, but we can't divide them. And this is where we use our trick for the identity matrix. Because what I now remember to do, hopefully, is I know that YA multiplied by A to the minus 1. Now, A to the minus 1 is nothing more than the inverse. Must be equal to this 5, 6, 7, 2, also multiplied by A to the minus 1. And the ordering of this A to the minus 1 is important. If you look, it's here at the end, and I've placed it at the end as well. Now y is a times a to the minus 1 important. We know that a times its inverse is equal to the identity, right? So that becomes equal to the identity. We know that any matrix multiplied by the identity is the matrix itself. So just finishing off the algebra here, we have y times the identity is equal to 5, 6, 7, 2 multiplied by the inverse of a. And we know that y times the identity gives me y is equal to 5, 6, 7, 2 multiplied by the inverse of a. Well, we know how to find the inverse of a. If we have a, what do? Well, let's work out the determinant. So the determinant of a is given by you multiply those two corners, so the 3 and the 6 together, which becomes 18, and you take away 2 times 1, which is 2, so the determinant becomes equal to 16. We now know then that a to the minus 1 is given by 1 over the determinant multiplied by, you swap these two over, so the 6 and the 3 swap over, and the 2 and the 1 become negative, right? You've changed the sign. So I can now use this information to say that y is equal to 5, 6, 7, 2 multiplied by 1 over 16, 6 minus 2 minus 1, 3. Well, that looks a bit odd, so we can happily move the 1 over 16 to the front, and that gives me 5, 6, 7, 2 multiplied by 6, negative 2, negative 1, 3. Now for information, you can't move this second matrix to the front because that would change the order and more importantly the value of the matrix that we would end up in. And for brevity, you know, you can either do that in your calculator or longhand, whereby what you do is top row times first column. Let's just use some colour. So we would use the top row times the first column, top row times the second column, bottom row times first, bottom times second. And what happens is when we do that, we get 1 over 16, and the multiplication becomes 24, 8, 40, and minus 8, which, if we wanted to write that in terms of fractions by multiplying everything by that 1 over 16, we get 3 over 2, 1 over 2, 5 over 2, and minus a half. So that equates to our value of y. Now this matrix algebra again is important because the inverse, and remember the inverse is this fraction multiplied by that whole doohickey of moving numbers and changing signs, it's all incredibly important. But there are questions, for example, where you may be asked to find ax plus d equals c, for example. Now that's not a problem because without having actual examples, remember we can add and take away matrices so long as they're of the same order, but we can't divide. So our matrix algebra in this case is what we would do is we would say ax is equal to c minus d, and we'd be able to work out what c minus d was. That would give me one specific matrix, and then whatever the answer to that is, we would have, right, well, assuming we wanted to find x, then what I would need to do is I would need to do a to the minus 1 multiplied by ax is equal to a to the minus 1 multiplied by the c minus d. We know that a to the minus 1 multiplied by a is the identity matrix multiplied by x, and that stays a to the minus 1 of c minus d. And then we know that the identity matrix times x is just equal to x. As much as I hate to say this, it's always a good idea in the examination just to show the examiner you understand these two stages and don't just jump, right? Now again, remember the order was important in this case. We put a to the minus 1 in front of the a, so we had to put the a to the minus 1 in front of the result of matrix C minus matrix D. Right? So I think that's pretty much what we need to know with regards to matrices, but why do we use them? Well, we come back to our good old friends, the simultaneous equation. If I have 3x minus 2y equals 5, and I have 5x minus 3y equals 9, I can rewrite this using matrix algebra. And what we find is that we have 3, -2, 5, -3 in a matrix. We can multiply that by xy, and what I get is 5, 9. Well, bearing in mind the whole point of this is to find the values of x and y, that means I need to move this to the other side. Well, remember, I can't move it to the other side. So let's rethink, and let's call this our matrix A. Let's call this x, and for some random reason, let's just call that C. So if I want x on its own, that means I would have to do a to the minus 1 multiplied by a multiplied by x is equal to a to the minus 1 multiplied by c. We know that this is equal to the identity matrix, and we know that the identity multiplied by x just gives me x. So to be able to find the answer to this, what it looks like I have to do is find the inverse of this matrix A and multiply by what I've got to C. Well, let's try and do that now. Okay, so we know that A is 3, -2, 5, -3. That's A. So what is our determinant? Well, the determinant is going to be 3 times -3, which is -9, minus 5 times -2, which is -10. Right? So -9 plus 10 would give me 1. So we would then have our fraction in front, our inverse would be 1 over 1, and I'm just going to write it in there for completeness. We swap these two corners, so the -3 goes there, and the 3 goes there, and we change the signs. So -2 becomes +2, and that becomes -5. So there we go. So that is now our a to the minus 1. And so we can find x by, well, 1 divided by 1 is 1, and we'll just leave that as it is. So it's -3, 2, -5, 3, multiplied by our matrix of 5, 9. And what does that give me? Well, working it out, -3 times 5 is -15, plus 2 times 9 is 18, so -15 plus 18 is 3. And then we do the same thing here, -5 times 5 is -25, so that's -25. 3 times 9 is 27, add them together gives us 2. And lo and behold, we know the answer to matrix X is 3 over 2. But as we defined X as X over Y, then I know that XY is 3, 2, and therefore my value of X is 3, and my value of Y is 2. Ooh, that's almost beautiful. Let's just check that that's actually true. So if X is 3, 3 3s are 9, minus 2 2s are indeed 2 2s, which are 4 obviously, which is actually 5, that works. And 5 times X is 15, minus 3 times 2, which is 6, which gives me 9, and there we go. An elegant solution to solving simultaneous equations. Now, one of the questions I see time and time again are the questions where you will be given two simultaneous equations and you have to find either a unique solution, no solution, or infinitely many solutions. Now, as I say, maths is a massive fat trick. It is there literally just to try and test whether you understand the language. If I ever see any of the words unique or no solution or infinitely many solutions, I know that it's got everything to do now with matrix algebra, all right, or matrices. Let's just think about it very quickly in terms of graphs. So, right, so you've got three different types of solutions. They're saying unique, no solution, or infinitely many solutions. If I look at simultaneous equations and go back to very basics, what is it? Well, simultaneous equation deals with straight lines crossing. If there is a unique solution, right, and we have this situation here, there are two lines that will have one unique solution. They cross in only one place. There is no way those two lines will cross anywhere else other than that one point. Okay? So unique means they cross in one place. What about no solution? Well, we're dealing with the idea of straight line graphs. Now, the only way that they will never meet is if basically both of them are parallel, right? So if they are parallel, it means they are never going to meet, which means the gradient of the two lines are exactly the same. We'll come back to that in a moment. So they're parallel. Right? So these will cross. And what about infinitely many solutions? Well, if one solution is where it crosses, no solutions are where it never crosses because they're parallel, I'm going to say to you that infinitely many solutions is where the lines fit exactly on top of each other. Right? Really bad diagram. But infinitely means that they are effectively the same line. Well, if they're the same line, then that should be pretty easy to test for. Well, it is. Now let's go back for a second, because we've got the general idea that, simultaneous equations are written in a different way. If I wrote down 2x plus 3y is equal to 6, for example, and I wrote down 4x plus 6y is equal to 12, what do I notice? I notice that all I've done to get from the top equation to the bottom equation is multiply absolutely every single term by 2. Well, if I've multiplied every single term by 2, all it means is these are exactly the same line, right? So there is a relationship between these points and there, right? So 2 goes to 4, 3 goes to 6, and 6 goes to 12 with exactly the same relationship. What about if I did something like 2x plus 3y is equal to 6, and 2x plus 3y is equal to 12? Well, in this particular situation, and I'm not going to multiply things around, but what we would actually find, well, actually, yeah, let's do it. If I was going to write this in gradient and intercept form, then what would I get? Well, I'd get 3y is equal to negative 2x plus 6, so y would give me minus 2/3 x plus 2, so that's this equation here. What would this second equation give me? Well, the same thing, we'd end up with 3y is equal to minus 2x plus 12, or y is equal to minus 2/3 x plus 4. What do we notice? We notice that the value in front of the x, which is our gradient, is exactly the same. So these things here have the same gradient and therefore are parallel. The only thing that seems to differ is the 6 and the 12, because that's what gives me my intercept. So we now know that for parallel lines, we are looking for these values in front of the x and the y to be exactly the same. Right? We're not bothered about this value over here, that doesn't matter what they are, but we need the values in front of the x and the y to be the same for them to be parallel. We need them to be a multiple of each other, in fact all numbers are a multiple of each other, and over here to have a unique solution, well, 2x plus 3y is equal to 6, and 3x plus 2y is equal to 12 will probably give us a solution, one solution. So now knowing that, how does that help us with our algebra? Well, I feel an example coming on. Imagine we have the line m minus 2x plus y is equal to 2, and we're told that mx plus 2y equals k. Ooh. And what the question wants us to do is find the values of m and k where there are unique solutions, where there are no solutions, and where there are infinitely many. Well, as I said earlier, having seen the language used here, I now know that what I'm looking to do is I'm looking to find values where I can make these values in front the same and different and multiples of each other. Well, how do we do that? It seems quite complicated. Well, actually it isn't, because first things first is we can look at this in terms of matrix algebra. If I rewrite this as m minus 2, 1, m and 2, then what I find out is that I can, just to finish it off, x and y is equal to 2 and k. Using matrices, we can work out the determinant, which actually helps us with some of this stuff here. So let's just do that first. What is the determinant? Well, if you remember, the determinant is given by these two corners multiplied by together, which is going to be 2 times m minus 2 minus 1 times m. So that's my determinant. Now, if this is equal to 0, what does that mean? It means there are no solutions. Right? If this is equal to 0, there is no solution. So let's just check to see what happens there. Right, what is the value? So that will become 2m minus 4 minus m is equal to 0. So 2m minus m is m minus 4 equals 0. So m equals 4. Right? So we know that for whatever value is, if m equals 4, there is no solution. Right? It can't have a solution because the determinant of that is 0, in which case none of this will work. So there will be no solution, i.e. the lines will be parallel. All right, so we know that the lines are now going to be parallel. We go back and use a bit of our knowledge from previous. Okay, so we now know that m equals 4 is actually an important value to us. How does that help us with this? Well, let's think about it. If we now substitute into our equation, we've got m equals 4, I'm going to substitute into these two equations, and what do I get? I get 2x plus y is equal to 2, and we know that 4x plus 2y is equal to k. Well, automatically I can see that this value here and this value here, this value here and this value here seem to be double each other, and what we decided was, from our previous screen, if we double all of the values, that means we're effectively having the same line, or infinitely many solutions. So we can now say that infinitely many solutions will arise where m equals 4, and that would suggest that 2 times 2 would be 4, k is also equal to 4. That will give me infinitely many solutions. But what happened if both of these were the same? If I have 4x plus 2y equals 4, and all I've done is multiply that equation there by 2, and leave this as 4x plus 2y equals k, we can now work out that parallel lines, we remember, are the x values and the y values, or the coefficient of both, are the same, but these cannot be the same. So there you go. That now helps us by saying, well, our no solution, or the one where there are lines of parallel, will be given by m equals 4, and k is not equal to 4. Right? So infinitely many solutions, m equals 4, k equals 4. No solutions, m equals 4, k isn't equal 4, and all of this was found by taking the determinant of this here. Right? So how will we know if the solution is unique? Well, if we have the same line or parallel lines, that was given by m equals 4. So if we want a unique solution, we can actually have m is not equal to 4, because m equals 4 gives us this determinant of 0. So if I have a unique solution whereby m is not equal to 4, then that means that k can be any real number. K can be any real number. As long as m is not equal to 4, k can be any value it likes. And there we go. This is used ever such a lot in exam questions, the idea of no solutions, infinitely many solutions, and unique solutions. Right? So just remember, you take your simultaneous equations, write them in matrix form, find the determinant, and this m, this value here, then helps you find out which are parallel, which are the same line, and which are unique. If you end up with a situation where you have simultaneous linear equations with more than 2 variables, all right? So for example, you have 3 equations, then you can't use any of the systems we've done previously. The good news is, just dive straight for your CAS calculator. It'll make life a lot easier for you. Well, I think that pretty much sums up the end of this video. Nice and short, but hopefully you've learned something.